Let's take a look at a simple harmonic motion problem of falling through a hole in the earth. So if you have the earth and you drill a hole on it, and this drawing is obviously not to scale, we have some person with a mass MP who's just going to step into the hole and just fall. We start with the assumptions that the mass of the earth did not change significantly when the hole was dug. So we're going to stick with the traditional mass of the earth, the three significant figures, as well as the radius to three significant figures. There's no air resistance or rubbing up against the sides of the wall as you're falling. And we assume a uniform density of the planet. If little r is the distance the person is from the center of the earth, so in other words, at the beginning, little r is equal to the radius of the earth, or big R, then the force of gravity is equal to g times the mass of the person times the mass of the earth 2 over r squared. So just classic force of gravity formula. Mass of the earth 2 is just the mass of the subset of the overall mass. So when the person is here, mass of earth 2 is the mass of the earth that is within that radius, as has been seen in a different video. The mass that causes the attraction when you're inside of a sphere of uniform density. The mass that causes the attraction when you're inside of a sphere of uniform density is that which is closer to the center than you are. Since the density is uniform, and density is mass over volume, then the mass is density times volume. So mass of the earth is the density times the volume of the whole earth, and mass of earth 2 is the density times the mass of the part of the earth that is within the radius of lowercase r. Solving for rho in the first one and plugging into the second one, we end up with this, and we end up with the mass of earth 2 is the mass of the earth times this ratio of little r cubed over big R cubed. Plugging that into our formula here, we get big G times the mass of the planet times the mass of the earth times little r cubed over little r squared divided by big R cubed, which ultimately ends up with a linear relationship here with this coefficient. The force of gravity, bringing some formality into it, is that the force of gravity is acting towards the center, in other words, in the negative r hat direction. And this piece right here is what we had developed on the other page. And that should be equal to mass times acceleration. And so mass times acceleration is equal to g mass of the person times mass of the earth over big R cubed times vector r, because vector r is just r times r hat. So we have this relationship here where the acceleration and the radial vector are directly proportional to the negative of each other. Thus, it's a simple harmonic motion problem. So we find a solution for it. So r hat is the amplitude, which would just be the radius of the earth, times the cosine of omega t. Just generically, v is just the derivative of this, or delta r over delta t, is negative capital A omega sine omega t, and then the acceleration would be negative big A omega squared cosine omega t. And if we plug that into our equation here, we have mass of the person times our acceleration is equal to our coefficient here, the negative of the coefficient there, including the negative sign, times r vector. We cancel out what we can, and we're left with omega squared is equal to big G mass of the earth over big R cubed. So omega is equal to this. That's the angular frequency. Now from math class, when I have a trig function like this, that the period is just 2 pi divided by omega, and so therefore it's 2 pi times the square root of r cubed over g mass of the earth. And then at this point, plug in the numbers, and we end up with 5,069.876 seconds, which is 84.498 minutes, so just under an hour and a half. And so that would be the time you jump into the hole, you get to the other side, and come back. So the time it takes to get to the other side would be half that, or a little over 42 minutes. Now in terms of units, just tracking the units here, we have, technically that's a radian in there, which is going to cancel out with another radian, but we have meters cubed over Newton meter squared per kilogram squared times kilograms. The kilogram cancels out. The meter squared cancels out with 2 of those. And then I have meters divided by this Newton per kilogram that flips up. So kilogram meters over newtons, and a newton is a kilogram meter per second squared. Those cancel out. Second squared flips up, and we end up with seconds in the end. So that is how the units work out. So anyway, this is the amount of time it takes to jump through the Earth, get to the other side, and come back.